Okay, thank you very much. It's a pleasure to be here, and pleasure to thank organizers for the invitation. Very nice town, exciting conference. So I will talk about some ideas that we've been developing for last few years with mostly with Cesar Gomez and also a bunch of students and postdocs. So this is about ideas trying to understand microscopic physics of black holes in general, and in particular this talk will be very much focused on information processing, how black holes process information. And so the very interesting thing that we find is that, okay, you can apply similar so what we understand from this picture, as you will see, I'll try to explain, is that there are other systems in nature which process information in a very similar way because of the certain property that they share with a black hole, in particular quantum criticality. And actually you can imitate black hole information processing in tabletop labs. And we are discussing with our experimentalist friends and they are actually, hopefully they will do this type of experiments. And that's very interesting. Anyway, so let me continue. And then if I have time, I will apply these ideas to the Sitter space, cosmological constant. And you will see, again, I mean, this can change pretty much the question, the way we pose question about cosmological term in general. Okay, so let me fix some notations. Now I will use speed of light to be 1, and I will work in these units. But I will keep h bar explicit because it's useful for this discussion. So therefore, this is the definition of the Planck length, which is h bar times g Newton, and Planck mass. And what is very important is that Planck length is intrinsically quantum. So if you keep gravity, strength of gravity fixed, Newton's constant, and take a classical limit, Planck length goes to 0. Now, let me start this introduction by a puzzle that you can create, and this is not a paradox, it's just a puzzle, okay? Which is, the interesting thing about this puzzle is that it's not based on any assumption. It's only based on the things that are extremely well accepted and well known in black hole physics. And when you try to put the two together, you see that you will get a puzzle. And by some reason, I've never seen this discussion. Cesar and I, we've never seen this discussion in the literature, at least in this way. Probably the reason is that usually in our community, we work in units, in Planck units. And if you work in Planck units, you miss this, okay? And so anyway, so we discussed this, and then we saw that this is a very good guideline for understanding microscopic structure of black hole information processing. Okay? Now, what is the puzzle? The puzzle is that we have two extremely well understood facts about black holes. First, we know that classical black holes, they don't carry hair. They're not very well known, no hair theorems about black holes, which tell us that if you have a classical black hole, there are very few parameters that define it. Okay, in particular, if you take a black hole, which is, okay, this is mass, angular momentum, and charge, and possibly some exotic new type of charges. And if you take a black hole which is not rotating and neutral, then the only characteristics is the mass. Okay. Now this means, right, from the point of information, this means that classical black hole carries 0 information, no information essentially. Okay, it carries 1 bit or something, yes or no, and this kind of stuff. Okay, because I cannot send you a message because it's featureless. And I cannot send you a message using a classical black hole because there are no features. I cannot encode anything in because message usually you write in features, right? Okay, this is a priori, this is not a puzzle. Black holes are special, but that's fine, okay? Now, there is another, so this is what I just said, right? So they are featureless. And after all, we can say, oh, usually classical objects, they carry infinite number of features, but okay, black hole is special. Now, there is another piece of information, which is, again, well known, which is Bekenstein entropy. Now, we know that quantum mechanically, black holes carry entropy. And this entropy is the area in Planck units. Okay. Now, again, this entropy, if the black hole is large, entropy is huge. But again, you can say that this is not a puzzle. So what? Quantum mechanics changes the story. So quantum mechanically now black holes acquire entropy. But the puzzle appears when you try to understand classical black hole as a limit of a quantum black hole when h bar goes to 0. Because that's what classical physics is, right? We assume normally that you recover classical phenomena when you take h bar to 0. Now, obviously, here if I take h bar to 0, black hole entropy becomes infinite. And that's a fact. Which means that now you have two facts. First, you have no-Heer theorem, which tells you that black holes are featureless in classical limit. And the second fact tells you that black holes as a limit of a quantum theory, again a classical theory, they carry infinite entropy. Okay? This means that they carry infinite amount of information. And both are true, because I didn't invent any assumption, right? Okay, so what is the resolution of this puzzle? And our idea about this, and we try to use this puzzle, because we are not trying to disprove it. This is correct, as you will see. But this gives you an extremely powerful guideline. What should be the microscopic degrees of freedom? What kind of properties they should satisfy that store black hole information, okay? In particular, the point is that these degrees of freedom should become, of course, their number. In other words, black hole stores information in some qubits. Okay, there are degrees of freedom in which you store information. I mean, any information you store in some qubits in quantum physics, right? Now, this number of the fact that entropy goes to infinity is telling you that number of these qubits becomes infinite. Okay, but simultaneously they must decouple. This is the way you can reconcile 0 with infinity. What happens? What happens is that it's true that in classical limits, black hole carries infinite amount of information. But it takes you infinite time to decode it. So this means that an observer that is observing a classical black hole for arbitrarily long, finite time cannot get any information because qubits are decoupled. You cannot probe them. And this is the resolution of the puzzle. Now, therefore, we know that the phenomena that underlines black hole information storage should incorporate this type of degrees of freedom, which have this amazing property that they simultaneously decouple when you take the classical limit. Okay? Very nice. So now I will, so in my discussion, I will do the following thing, okay? I will present the story from the point of view of a person or a physicist, okay, that first learned quantum mechanics and then learned classical physics, okay? So suppose you educate a child, and the child only knows quantum mechanics, most fundamental thing, and for this person, classical physics is a limit of quantum mechanics, okay? Now, the question is, how would this person try to understand black holes, okay? Not the other way around, okay? From quantum to classical. This will be my discussion, okay? So I will try to be in this position. Now, the person that knows quantum field theory, or quantum mechanics, knows that the building blocks in quantum field theory are particles, okay? There is nothing else. They are particles and their interactions, okay? Everything should be, you should be able to understand any phenomena as a phenomena with particles, either many or few, and that's a separate story. Weakly coupled, strongly coupled, or whatever, but particles. Now, in black hole physics, you can safely choose vacuum to be Minkowski, okay? Why? Because we know that black holes you can produce in the particle collision. I mean, nobody disputes this fact that you can produce black holes in particle collision. You can collide two particles, produce a black hole. So this means that you know that the vacuum of choice of Minkowski must be a consistent choice, okay? Of course, you can choose other vacua. That's a separate story. But Minkowski must be a consistent choice because you can form black holes in S-matrix formulation. This is, again, a well-established fact. There is no assumption here. Therefore, this physicist has to understand black holes from the point of view of the vacuum and the particles that you create on this vacuum. Now, for simplicity, let me stay in a theory with pure gravity, okay? In a theory with pure gravity, pure Einstein gravity, but viewed as a quantum theory, okay? Now, in Einstein gravity, if you view it as a quantum theory, it's a theory of a single propagating a particle, okay, with spin 2 and 0 mass. And this particle has a very interesting property of, now, as you know, in quantum field theory, we characterize particles by their strength of their interaction, their quantum interaction, or the same thing that gives us the amplitude of 2-to-2 scattering, okay? Now, this strength of the interaction of gravitons is very special because it depends on the de Broglie wavelength of momentum transfer. In other words, it depends on the wavelength of gravitons, okay? And therefore, and actually this alpha, which I will call alpha, sometimes I will call it alpha gravity, alpha is literally a ratio of the Planck length to the wavelength of the graviton squared, or which is the same thing as momentum transfer divided by Planck mass squared. Now, this immediately tells you this expression, okay? What are the domains in quantum gravity where you can be under control, okay? Right? So usually in quantum field theory, domains where we can be under control are domains in which particles are weakly coupled. If coupling is weak, then I can compute reliably in some perturbation theory. I need some small parameter to expansion. Now, domain in which you feel comfortable in quantum gravity, and you can do reliably some computations, I'm not saying everything, of course, is when the wavelength of gravitons is much longer than the Planck length. Wavelength of gravitons involved in the process of your interest. So for example, if you take gravitons of 1 centimeter wavelength, the coupling is incredibly small. So this is much better theory from the point of quantum field theory than quantum electrodynamics, right? Because coupling is almost zero. It's like almost free theory. So therefore, in my discussion in what follows, I will stay in the long wavelength graviton domain. Of course, there is a domain in which we are out of control, where R becomes of order L Planck. Of course, there you need ultraviolet completion of gravity, because in effective field theory, we don't know how to compute amplitudes with short wavelength gravitons. You can choose your favorite UV completion. Could be string theory or loop quantum gravity, or you can invent something else. What I will say, because I will stay in the domain of long wavelength gravitons, will be insensitive to the UV completion. Okay, whatever takes care of the short wavelength phenomena will not. My results will not depend on that. So I will try to be in the domain in which we are under good control of effective field theory, and I will give you proof of this as a consistency check. Okay. Now, from this point of view, the only candidates that can store black hole information are collective degrees, must be some kind of collective multi-graviton degrees of freedom. Okay? So therefore, our assumption that we are making, the starting assumption, of course, in any theory you have to make an initial postulate, right? So our initial postulate is that black hole, from the point of view of such a physicist that only knows quantum theory and tries to understand classical physics from quantum theory, black hole is and must be a multi-particle state of soft gravitons. Okay? In other words, the bulk of physics of information processing should come from soft graviton physics comparable to the classical size of a black hole. In other words, things like singularity, short distance physics should not play important role in information processing. Okay? This is our starting postulate. Of course, there is a community that there are people that assume otherwise. You can also assume that the entire thing about black hole information is in the singularity. This is a different road. I'm not taking that one. Okay? Now, The point is, however, it turns out that the moment you make this postulate, the black hole is a bunch of soft graviton state, it's a soft graviton state, it turns out that these gravitons are at an extremely special state of so-called quantum criticality. That's not an assumption, that just follows, okay? So the moment you say that these are a bunch of gravitons, they are quantum critical. Now, they are quantum critical, and what is the physics of this? Is that their number is exactly 1 over their coupling, okay? By the way, notice that the coupling of gravitons goes as area. This is a fact. This is not an assumption. It's a fact of nature that the coupling of gravitons, quantum coupling of gravitons, goes like area. And in our approach, this is where holography is built in. This is the source of holography. This is just a fact of nature. In any dimensions, graviton coupling goes like area. That's why in our theory, in our explanation, the holography enters because the entropy scales like area, because entropy scales like inverse coupling of gravitons, okay? Yeah, that's a fact, right. It's always like that. It's always area in that dimension. So it's always codimension 1, area, surface area. Sorry? No, I'm saying that, yeah, but I'm saying that in any dimension, so if you have 4 plus d dimensions, the coupling will be 2 plus d. You are disputing this statement. No, then I don't understand the question. So what is the question? You are saying that it's true that what you are saying is true, yeah. It's set by the dimensionality of Newton. If it's deep. No, that's up to you to decide. I'm giving you an observation. Everybody is puzzled about holography, right? We have mystified this holography. I'm telling you, there is an observation which nobody noticed. I have never seen this observation even mentioned in the literature. Now, the observation is that the graviton coupling scales like area. Of course, you need a microscopic theory which promotes this observation into something deep about entropy. This is what's happening in this theory. Of course, for that you need a microscopic theory. But I'm saying in general, there is this observation, which is, and the reason why in our case, entropy scales like area, because entropy scales like inverse graviton coupling. And then automatically it scales like area. Okay, that's the exactly, but that's of course peculiarity of this description. I'm not saying that it's true in general, but I'm saying in this description, right? Now, okay, let me give you some starting indication. Why would you think that black hole should be n soft gravitons? Okay, okay, you can invent many different thought experiments, but I don't have time, of course, to go all of them. But think about a very simple thought experiment. Okay, I mean, this thought experiment is the following. Again, I mean, suppose I tell you, okay, take some imaginary box of certain size, lambda, okay? Some imaginary box, like 1 centimeter, let's say, or 1 kilometer. Now, of course, everybody agrees, and this is well known, that if you put enough gravitons in this box, you will form a black hole. Now, let's ask this question, I mean, how many gravitons should I put in the box so that classically I would conclude that this is a black hole, okay? Of course, energy is quantum mechanical of gravitons. Then the mass will go like n divided by the h bar divided by wavelength, and you recover immediately that the number of gravitons for which you form a black hole is 1 over their coupling. So again, another fact of nature. So if you put together number of gravitons give equal by inverse of their coupling, you will form a black hole. Again, this is not an assumption. This is just a fact of nature. Okay. Now the point is, what interests me is what is happening microscopically when you form a black hole. Why is this a special place when n is equal to 1 over alpha? Okay. And now, what is the reason why it's a special place, quantum mechanical, now I'm discussing quantum mechanically, is that this is the place when the gravitons can hold each other. Okay? So in other words, if you put 2 gravitons in the box of 1 centimeter size, they don't even see each other because the coupling is so weak that they will just rarely scatter. It takes actually 10 to the 114 or some enormous time scale years to scatter them. Okay? So when n is 1 over alpha is the place when gravitons they realize when they see the collective effect of each other and they hold each other. Okay. Yeah, you do here also, right? That I'm not. No, I mean, I'm just saying, take a gravitational field of the Earth, for example, right? You can think of it as a coherent state of some gravitons. But those will not be at the quantum critical point. That's why you need Earth to keep them together. Okay, so so gravitational field of the Earth will be the number, or it will be enormously smaller than 1 over their coupling. Okay? Okay, so that's, otherwise it's correct. So that's why you need Earth. That's why Earth is not a black hole. But when you collapse Earth into a black hole, what happens with the constituent gravitons that their number becomes 1 over a coupling, and they no longer need the source. Okay, they can keep each other together, right? So this is basically the point. So alpha is a very special place, and so quantum mechanically it's a point of phase transition. But of course, this phase transition is not thermal. It has nothing to do with the temperature. This is simply your system is in 2 different phases. This phase is when a system wants to, the ground state is very close to free gravitons. Okay, you need a source to keep them together. You need a box or an Earth or something. And when the ground state is different. Okay, this is the transition point. And as usual, as you know very well, at the transition points, especially at quantum critical points, a lot of interesting phenomena happen. In particular, what happened is the system has to rearrange itself. Okay? Because system has to rearrange itself, typically a gapless modes appear. Okay? And it also is happening here. But because graviton coupling is derivative type coupling, right? Because gravitons couple, it turns out that the number of gapless modes is enormous. Actually scales like 1 over alpha. Okay? So pictorially, this is what is happening. If I think of this graviton gas, let me call it a gas. Of course, it's cold, as I said. And here I plot alpha n. So Earth would be somewhere here. Okay? So for example, if I would compute, and Earth typically would have quantum levels will be spaced by inverse size of the Earth, okay, or something like that. But once you move towards the black hole phase, it turns out this is what happens. Enormous number of modes collapse and become almost gapless. They become almost gapless up to 1 over n again, okay? Now, I mean, we find this to be an extremely interesting phenomenon of nature, okay? Okay, this is the way a system stores information very cheaply. Because you see, normally if you tell me to store a bit of information in the box of this size, I need energy 1 over this size, okay? Right? But not for a black hole, because for a black hole, the gap is suppressed by 1 over n. So it's an extremely cheap qubit. So it's like almost free to store information. It's almost free energetically, but then there is a price to pay because you need long time to decode it. You see, there is no free lunch anyway, all right? You store information cheaply, but you need price to pay, all right? So the qubits that store information are Bogoliubov or Goldstone modes of this graviton condensate. So basically, there is a symmetry, underlying symmetry, which acts on the graviton constituents of this condensate. And this symmetry is spontaneously broken by the condensate. And the quantum critical point is the point when goldstones become gapless. When you move away from the quantum critical point, this symmetry is also explicitly broken. So in other words, the spontaneously broken symmetry becomes almost exact at the quantum critical point. This is another way to think about it, okay? So you have enormous number of Goldstone bosons. Now the effective Hamiltonian, okay, schematically, has this form. Now you can derive it, okay? So from here, you just go ahead and derive the effective Hamiltonian of these modes, okay? Using usual many-body methods. We developed also new methods. Thinking about this, you can use Bogoliubov approximation, but we developed new methods. On its own, it's very interesting to play around with this critical point, okay? No, here no assumptions. You just you give me a gas of cold bosons in a box, let's say, okay, and I move them to the critical point, and I just try to analyze collective degrees of freedom of these bosons. Basically, try to rediagonalize Hamiltonian. No, that you derive. You see that it becomes 1 over n. That's not an assumption. In other words. You start with a many-body Hamiltonian in a generic point. You don't have to start at the critical point. You start with a many-body Hamiltonian. So let's say at this point somewhere here. For example, here essentially this Hamiltonian corresponds to the gas of free gravitons. When essentially their number is so small that coupling plays essentially no role. And then you have two parameters to play with. Okay, in alpha n and n, or alpha and n, depends how you choose them. And then you gradually move to the critical point. Of course, you can analyze the spectrum at every point. And you see what happens with the spectrum. You see what happens with collective degrees of freedom. You see this explicitly, they become gapless. Now, as I said, we developed several methods. Now, for example, Golubov method was known. Sorry? I have an initial Hamiltonian in terms of gravitons. No. Graviton interaction through the energy momentum tensor. Okay, but the point is that what is interesting. I will talk about that. What is interesting is that this phenomena turns out to be essentially independent of the details. Like what is important is the gravitons are attractive, and that they are derivatively coupled. Okay, essentially it turns out that if you hook up Bose-Einstein condensates which are attractive. Then you always have gapless modes, and if they are on top of it derivatively coupled, you have enormous number of gapless modes. Okay. Well, gluons, it will work if you manage to create a situation in which gluons can be in this situation when 1 over alpha is 1 over n. Gluons also have repulsions, therefore you have to be a little bit careful. We didn't study this for gluons. It's a good question. Because they are not only attractive. So gravitons are always attractive. So, but for example, if you invent some scalars which are attractive and the derivative coupled is exactly the same phenomena. Okay. So the bottom line is that the effective Hamiltonian of these qubits has the form where epsilon goes to 0 when n goes to infinity. And literally, you reproduce what you expected. You see that these qubits decouple and going to infinity limit, and they become gapless. Okay. So essentially, in this description, black hole is an n-long message of zeros and ones composed out of this qubit, superposition of this type of states. Okay. Now there are immediate consequences of this scenario. Okay. And let me list most important ones for this discussion. Now, what are the most important ones? First, as I said, black holes carry hair, and amount of hair becomes infinite when n goes to infinity. Okay. But the time scale to decode this hair also becomes infinite. By the way, to decode this hair, you don't have to wait until black hole evaporates. That's one possibility. But in this picture, you can simply do a scattering experiment. You can scatter, for example, a long wavelength radiation at a black hole and then decode it. But again, because qubits are extremely weakly coupled, it's extremely hard to resolve them. So the time scale goes to infinity. Okay. Now, for example, this is pictorial description. Also, in particular, this hair can encode information about global quantum numbers. So in this picture, these Folk theorems, you know that there are these Folk theorems that black holes should violate global charges. The argument on which these Folk theorems are based is wrong, because they are based on certain arguments that black holes do not carry hair, right? Here it's wrong. Manifestly, you can have conservation of global quantum charges in this theory. There is absolutely no problem with that. I'm not claiming that you cannot have other reason why global quantum charges can be broken. Of course, you can have other fundamental reason for even coming from quantum gravity. I'm not talking about that, but I'm saying the Folk's theorems based on black hole, this argument that you throw in baryons and then they cannot come out and this kind of stuff, this is wrong because it's based on no hair theorem. And here is an experiment. So suppose I have a condensate of this, let me call it a condensate of these gravitons, and I throw a baryon. Okay. Then this becomes an impurity in the graviton condensate. This impurity I can measure by scattering a long wavelength baryon, let's say. Of course, we are in hypothetical theory. In reality, baryons are massive, but which makes it more complicated technically. But if you scatter a long wavelength baryon, then you can see that there is an interaction. Of course, this is extremely suppressed. So you need an extremely accurate apparatus because this is suppressed by baryon number over the graviton number. But it's measurable. I mean, there is a normal scattering quantum experiment which gives you 1/n correction to the hair. By the way, right, let me finish first this. Second point is that the Hawking radiation, okay, what is -10? What does it mean? -10 means that. I thought, yeah, okay. I thought I was over. All right, okay. But we started a little bit late, right? Yeah, okay. All right. So now the point is that the Hawking radiation cannot be exactly thermal in this approach, okay? And I claim that this is the mistake that everybody that talks about information paradox is making, that corrections to Hawking radiation are not exponentially suppressed, they are 1/n. And that's a fact of nature. And this 1/n, once you accept that Hawking radiation is not exactly thermal and there are corrections to it, the entire basis to talk about information paradox is abolished. Okay. Now, there is a third thing, an important phenomena of quantum break time. What does it mean, quantum break time? Quantum break time means that any quantum system has a typical time scale, after which quantum evolution of expectation values is no longer tracking the classical equation of motion. Okay, so this is a quantum break time. Now, this is true for arbitrary system, but what is important, because the black hole is at the quantum critical point, quantum break time is not exponentially long, it's extremely short, it's a power law. Okay? Now, there are two types of quantum break times, and by the way, this also is a consistency check for this picture. Now, the first quantum break time is so-called information scrambling time. So we have computed the information scrambling in critical condensates, okay, of attractive bosons. We showed that this quantum break time, the scrambling time goes like logarithm. Now, this was a conjecture long ago by Hayden and Preskill, not so long ago, but okay, relatively long ago. They suggested that the black hole should be fast scramblers in logarithmic time. But there was no microscopic theory of a black hole to verify this. And we see that this is true. Explicitly, we see that there is a logarithmic time. Now, what is scrambling? Information scrambling is basically how fast your system can store the message among the constituents, okay? And this is, it could be a diffusive process. If somebody walks in this room and asks you, tells you something, and then you spread the rumor among the nearest neighbors, or it could be an announcement. And this is what black holes do, okay? And okay, but now what is also very interesting is that this property is purely a property of quantum criticality, okay? Because we checked this for many different systems, and here is an exactly solvable model. I mean, you can diagonalize Hamiltonian exactly numerically. You take even a simplest Bose-Einstein system at the quantum critical point, okay? Sorry. And you see that this system, for example, you see these Bogoliubov modes going down, etc., etc. And the scrambling time is logarithmic, all right? So this tells you that this scrambling logarithmic, fast scrambling property is not an exclusive property of black holes, but it's a property of Bose-Einstein systems with attractive bosons at quantum critical point. And you can build them in laboratory. Now, this is another picture, which I think is one of the most important things about this, illustrates the point. Again, yeah. It doesn't matter. Doesn't matter. Universal. It's always log. Which will dimensionality changes the prefactor. This is what we are. I mean, we cannot prove a theorem, but this is what we are discovering. So what we are discovering is that dimensionality only changes the prefactor here, this prefactor, okay? But the log is there, And what you need is that system has Lyapunov exponent. In other words, these quantum critical systems have Lyapunov exponent. By the way, now people are coming to it because there were papers, again, repeating essentially the same statements. That Barbon, I don't know, but yeah, I don't think so because we discussed this thing with him. He never mentioned, so I don't think he had the same thing. But anyway, okay, you can tell me more. No, what matters is the Lyapunov exponent, because the point is that in the overcritical regime here, right, slightly here, system has Lyapunov exponent and becomes a fast scrambler because it develops chaos and becomes a fast scrambler. And now it sort of is penetrating in the community that the chaos and the Lyapunov exponent, you can see the dimensions over and over again. The point is that I have not seen any other microscopic model on top of this. People mention these words, but the microscopic model so far I know is the quantum critical condensates with attraction. Now the thing is, now this is another very important thing, and let me explain this carefully, because this is an entanglement computed at the quantum critical point, okay? Now you see what happens. So this is the phase where you would have a normal planet, okay? And this is the point of black hole. Now what happens here is that the entanglement becomes enormous. And you see that entanglement is increasing with number of particles. So bigger is the black hole, more entangled is the ground state. So you see, ground state of this system here, so ground state here is very close to classical. That's why, I mean, Earth's gravitational field, the ground state of the is very close to classical. But the ground state of a black hole system is maximally far from classical. It's maximally entangled. But black hole takes a very long time to reach the ground state. So you see, this is the point. The moment you form a black hole, it's classical in very good approximation. To reach this point, the growth of the entanglement takes power law time in n, which is enormous time, okay? And this is the point. So this gives you another time scale of quantum break, during which black hole becomes a maximally entangled state of the constituents. So what happens there is that this is the time scale which goes n3 half, okay, which is essentially comparable to the half evaporation time of a black hole if you translate in the familiar language. But we understand what is happening after that. What is happening after that is the black hole, if you think in this 0 and 1 language, is a superposition of these zeros and ones with exponentially large number of terms. Okay? So it's a maximally entangled state. It's not EPR pair or anything like that. It's not like 0, 0, 0 plus 1, 1. No. It involves exponentially large number of terms. And essentially it's maximally quantum. Okay? Why? Because expectation value of the operator is maximally different from what you were expecting in classical GR. Now, by the way, it's a very interesting question. What's the right description of this in terms of mean field? We didn't study that so far. But, of course, it continues to be soft gravitons. Now this picture, so recently we asked this question, okay? The question was, okay, we know that the black hole, classical black holes has infinite hair. We know quantum mechanically who are the information carrier degrees of freedom, Goldstone modes, okay? And then was a natural question to ask, if I take a limit of large n, classical limit is infinite n, is there a geometric meaning to this symmetry, okay? And okay, there was a story recently, people started thinking about BMS symmetry of Minkowski space. And we were thinking in that direction. We were wanting to reconcile this with whether there was a BMS symmetry. Indeed, we showed that for Minkowski, you can do exact matching. In other words, in our picture, Minkowski is an infinitely massive black hole, okay? And for infinitely massive black hole, when R goes to infinity, N goes to infinity, to the leading order, we can show that the symmetry, the Goldstone symmetry that moves around Goldstones, is BMS symmetry. Then we made this, then of course the natural realization was that for a finite size black hole, if you take classical limit but you keep size finite, again must be some modification of BMS symmetry. This is not known in the literature. And meanwhile, a paper by Hawking appeared, one very short paper. He is not discussing the wavelength of Goldstones, But what we claim is that the wavelength of the ghost should be given by R in that limit. There must be some modification of BMS. I mean, he's not discussing any details. If I understood correctly what he wants to say, I think partially agrees with what we are saying, partially disagrees. Because what we claim is that you cannot read information unless n is finite. If n is infinite, in the classical limit, it's not true. Even though there could be black hole can have a classical hair, BMS hair, this hair you cannot decode information just by looking at this hair in classical limit unless n is finite. You have to take into account finite n effects, okay? Information content of Minkowski is infinite because, you see, first of all, Minkowski is a highly degenerate state, okay? Because Minkowski you can obtain as various limits of black holes, for example, right? One thing is that you can think of Minkowski as a limit of an infinitely massive black hole, right? Because all the curvature invariance goes to 0 in that case. Even classically, you can think in that way. And locally, you always have Minkowski, right? But of course, infinitely massive black hole has infinite information, even in quantum theory. You don't have to take classical. So Minkowski in quantum theory already has infinite information. Now, we see this explicitly in our construction because we see that the Minkowski becomes a coherent state of infinite wavelength gravitons when we take n to infinity. And we can exactly match this with this BMS symmetry. Just becomes infinite wavelengths. That's it. It still stays at the critical point, but yeah, critical point is always alpha times n is 1. So you have a condensate of infinitely many, but infinitely weakly coupled gravitons. Okay? So in direct sense, even classical, right? If I think of infinite mass black hole, all the curvature invariants go to 0 at any finite neighborhood, right? If I'm well, unless I'm at the singularity, right? At any place, yeah, inside or even outside. Even outside, I mean, all the curvature invariants vanish when the mass is infinite, right? Curvature invariants, like whatever, right? They go like 1 over the Schwarzschild radius, some power of 1 over the Schwarzschild radius. So, yeah, so that's okay because you see, the total mass is infinite, but also space is infinite. So the integral is finite, but the space is so large, you spread infinite mass over much bigger space. So you don't see the thing, yeah, right. I mean, we have an explicit construction of Minkowski as a coherent state. You can just construct Minkowski as a coherent state very rigorously in using quantum field theory rules. Right, and so, as I said, this sort of matches what Hawking is saying in the paper, if I understood it correctly, okay? But there is this important thing of finite n. Now, the point is that there is a okay. I only have 2 minutes or something. Let me converge here. So again, I mentioned that this also opens up a very interesting possibility of doing black hole type quantum computing in tabletop labs. Because you see, now I told you, most of the things come from the quantum criticality. But in tabletop labs, we can create these quantum critical condensates. We can even manipulate. We can move close to the critical point, away from the critical point. And we can construct some logic gates and literally do quantum computing through the same physics that black hole does, okay? And this is very exciting. For example, we developed in a recent paper with a student of mine, Misha Panchenko. This is this analytic method of entropy growth for this system. Entanglement growth. And you see that indeed this entanglement growth, the time scale for entanglement growth becomes longer and longer with large n. So it's powered low with n, okay? So in other words, if you're in large n limit, you form a black hole, you have to wait extremely long before it becomes entangled, okay? So again, there is a full continuity. All right, so this is state evolution and fact like that. And let me just flash for the beginning the transparency. One transparency, because another very strong evidence that we are on the right track is in black hole production in the graviton scattering. Because this is a long idea of black hole production in graviton scattering, was pioneered by Toft and others. That if you scatter very energetic particles, you form a black hole. It's there is a consensus that this is happening. The problem was that nobody understood how this two particle state all of a sudden becomes this highly entropic state and things like this. And for this you need microscopic theory. And now we have a microscopic theory. So of course it's a natural thing that we identify what is the right process for black hole formation. This is 2 to n, not 2 to 2, but 2 to n. And we did this computation with our collaborators, a bunch of people, okay, with these people here, right? We computed, now we did this computation in fully fledged quantum gravity on one side and string theory on the other side. And the results are the same in this kinematic regime, okay? So you see that you indeed reproduce entropy suppression in 2 to n graviton scattering of doing fully fledged quantum computation in this domain. Now in this domain, quantum gravity computation is fully under control. It's a very nice computation actually, because we are in 1 over n. We use 1 over n, it's perfectly reliable, okay? And that's another thing. So these two, field theory, the quantum field theory, things agree. Okay, so let me finish here because I don't have time to apply these ideas to lambda. Okay, thank you very much.
Okay, there's time for a couple of questions.
Yeah. A question about this last scattering, because there are some papers of Steve Berger himself saying that in the collinear limit, that I think is the case, especially in Reg limit, you can substitute in the 3-level scattering amplitude 1 graviton with 2 gluons. So my question is...
yeah, that's a very excellent point. Right.
It could be very interesting to consider scattering amplitude with n gravitons and n gluons.
Exactly. We are trying to think about that, the same group of people, okay, with plus minus 1 variation.
Because me and Massimo Bianchi, for ourselves, we have calculated.
Right, very good. So, excellent. So it's a very good point. I mean, because we want you to understand in this way formation of black holes with impurities. Okay, with some admixture of the, for example, gluons. You not only form gravitons, but you also form gluons, or in gluon scattering, production of black hole, and this kind of stuff. Yeah, it's an excellent point. It's we are thinking about that, trying to use the same technique for computing that. Yeah, exactly.
There's time for another quick question.
So can you tell us just a little bit about the sitter?
The sitter.
How does this look?
Right, very good. So the natural thing will be whether you can generalize this thing to the sitter, okay? And of course, this would be very important because of the question of cosmological constant. I'm not saying that this is solving the problem, but this is changing the question, because we are normally asking this question whether cosmological constant, why it's so unnaturally small, but we are not asking question whether cosmological constant is even consistent quantum mechanically. And so the point is that you can apply this idea of trying to map the sitter space on, again, multi-graviton state. Again, I want to warn everyone that this is an assumption as compared to black hole situation. Okay, this is an assumption. Why? Because black holes, we are in very comfortable situation, because black holes we can really form. We know that we can form them in a scattering experiment, but at least theoretically. But the sitter has no asymptotic, usual story that the sitter is not. So it's an if. There is this question whether such a picture for the sitter is applicable. But if it is applicable, if we assume that, then it's the same conclusion stays for the sitter, that the sitter must have a finite quantum break time, which means that there is inevitably, I can show you last. Inevitably, there are processes which will take you. First, you will see that the sitter is also close to quantum criticality, and secondly, the sitter has the same quantum break time. Now, this means that after this time scale, you can no longer describe classically the sitter. But if you cannot describe classically the sitter, obvious question appears. Then what does it mean to have even cosmological constant? Because cosmological constant is an intrinsically classical object, right? It's just a constant you are putting there as a classical source. And so maybe there is some key to understanding cosmological constant issue here. Of course, what it is, we don't know. But we know that there will be finite quantum break time and the sitter will evolve. So in other words, there is no classical eternity. The moment you say that the sitter is a quantum state, classical eternity is abolished. Okay, so quantum mechanics plays its own game. This was the point.
Okay, I think we should thank our speaker again.
Okay.